So I know a few of you, or at least one of you mentioned that you had started the tutorials for the PAs and couldn't find the models. I thought that they mentioned where they are somewhere in the tutorial, but on the off chance they didn't, I used my handy find command in Linux and got it for you. I'm going to put that in the chat here. And I'll also post it on Canvas a bit later on. Let's see, where's the chat? Okay, you'll right now you'll notice that cadence is down. That is well, short story. The license server is not working. All right.
What about the backup license server?
Backup.
Or a very like
you actually want to survive this trip with a back? Yeah. You want redundancy?
Surely we spare one computer per.
Well, we could, but then they asked to raise your comprehensive fees, and so it's just a. Anyhow, I put the path to the model in the chat. Now, let's see if it'll let me do this. If you wanted to add that path, if you have a simulation window open, you go to Setup Model Libraries. And it's probably not going to let me do this, but you would add that path into one of the model libraries. Oh yeah, it's going to tell me I don't have a license, but I could put that path in and uncheck my other model library, and I'd be good to go if I wanted to run the PA tutorials or the LNA tutorials for that matter. Any of the tutorials, all the models are in here. Okay. The license server is down. I'm told that it will be back up tomorrow. Apologize. I'll do everything I can to accommodate. Don't worry, I'm a pushover, so I'm aware of the deficiencies of the IT support in this department, and I will not penalize you for that. All right, where were we? Okay. So we've been looking at Class E power amplifiers, and came up just in a review of the paper on Class E power amplifiers by SoCal. They tell us that the Class E power amplifier needs an optimal susceptance that's presented to the drain of the transistor. It has a value of 0.1836 divided by whatever R-opt is. R-opt would be determined by selecting the proper, or by determining what output power level you want and just inverting that equation for P out. Once you have R-opt, you can get B-opt. This is a positive susceptance, so it means that you need some capacitance at the drain of the transistor. The transistor itself is going to be fairly large. Typically, if you're trying to get a lot of output power out of these things, it's going to be on the order of a few millimeters of width at a minimum length. So it's going to naturally come with quite a bit of capacitance, but you still might need to add some extra capacitance in order to achieve the optimum susceptance that you're looking for at your switching frequency. And then looking towards the series resonant network, you need a network that is series resonant. So that's if we go back and look at the schematic. Okay. We have a series resonant network. So that's series resonant at the switching frequency, and then there's some excess inductance that forms this X-opt. Let's see, is my pen not going to work? Oh, goody. Okay, that pen will work. Good. Good to know. Okay, anyhow, you have some X-opt. This is just some excess inductance. Now, with a Class E network, you can, this series resonant circuit with some excess inductance can be realized with a matching network. So you're probably not going to just make a series resonant circuit. You're going to do an impedance transform. That impedance transform is going to have a finite bandwidth. It's a narrow band circuit, and so that can serve as this filter. Okay, so how do we size this switch for a Class E amplifier? So, when we were sizing the power transistor for a PA, it had to do with basically the current driving capacity of the transistor. We needed to make the device wide enough that it could drive enough current. Here, we're just going to try and drive the on resistance of the device down. So, we modeled the Class E amplifier. We have maybe an ideal switch with some resistance in series with it. Of course, we can make an equivalent out of a MOS device. So here's our MOS device. And of course, our MOS device ends up having some drain to source resistance. So, ideally in the off state, ID goes to 0, no current is flowing through it, so it's just in pure cutoff. But then when we turn the switch on, it's going to go through saturation, but ultimately the drain to source voltage is going to be driven to be pretty close to 0. So it's going to go into triode. Basically, that's what happens with any switching amplifier. It goes back and forth between cutoff and triode. In between those two states, it's in saturation for some brief period of time. All right. So in triode, we know that the drain current for our MOS device is equal to mu in C aux times W over L times VOV minus VGS minus VDS squared over VOV. RDS is equal to the partial derivative, the inverse of the partial derivative of the current with respect to the drain to source voltage when the drain to source voltage approaches 0. And so we can say that RDS is equal to 1 over mu in C aux times W over L times VOV. Okay. All right. So generally VOV is fixed in a switching amplifier. We're not going to change the amplitude level. We're just going to drive the switch, the input back and forth between the supply rails. We're going to drive this with inverters or something along those lines. So something very digital in nature, just back and forth between 0 and VDD. Okay. So you can show that in a Class E power amplifier, the resistance, the power dissipated in the resistance of the switch is equal to 8/3 whatever the switching resistance is times P out over VDD squared. And then the power that we dissipate at the end. So this is what we would call in a power electronics course conduction loss. So this is the loss that happens due to resistance in the channel of a MOSFET, or the channel, or we can technically do this with BJTs as well. So it could just be in the emitter to collector path. Now at the input, we're also going to dissipate power because we have some large gate capacitance to switch. So Pn is equal to 1/2 CGS times VDD squared times F S, where Fs is the switching frequency, the RF frequency that we're going to operate at. So typical 1/2 C VDD squared F power consumption. And what we see fairly immediately from this is the switching resistance, we see comes from the drain to source resistance formula. Oh, sorry, the input power they call switching losses. So again, if you're talking about power electronics, they talk about balancing your conduction losses and your switching losses. Switching losses are due to switching some capacitance. Conduction losses are due to ohmic losses from resistance. Yeah.
How come the conduction loss has a VDD term in the denominator? Like, I would think that is just like.
It's just a normalization factor that has to do with how they. There's a fairly long derivation for this, but it's P divided by VDD.
Yeah.
And P is proportional to VDD, so that kind of cancels out, right? Okay, so this resistance is proportional to 1/W, and this capacitance is proportional to W. And so that kind of tells you that there's going to be an optimal size for the switch. If we want to reduce the conduction losses, it would tell us just keep making the switch bigger and bigger and bigger, and you'll arbitrarily drive down the conduction loss. But as you do that, you're going to arbitrarily start driving up the input power. And so there's a trade-off between when those are optimal. Typically, in most switching applications, you can show that the optimum occurs when the input power is equal. The switching power is equal to the conduction power. So when I make those two equal, that's typically when the transistor size is optimal. All right, so the total power that this thing is going to consume is going to be the output power plus the switching, or plus the conduction losses. And for simplicity, I'm going to omit other forms of loss, but technically I would also need to add in my input power and my maybe matching network losses, so power lost in the matching network. And all of our other losses are going to be added here, but we want to come up with a relatively simple expression for how to size the switch and how to size the optimum termination resistance to guarantee that I get a fixed amount of power. So I can make some substitutions here. We're in that dark blue color again. Let me fix that. All right, so we make our substitutions, 0.577 times VDD squared over R opt plus 8/3 R switch times P out over VDD, quantity squared. And then we invert all of this, and we can show that R opt, in order to deliver a specific amount of power to the output. I realize what I did here. I don't want to include this because it's not affecting the output power. Only the loss in the matching network is. Okay. So if I want to deliver a specific amount of output power, factoring in that the switch has some conduction loss in the output, I can solve and say that R opt is equal to 0.577 times VDD squared over P out minus 2.67 times R switch. Okay, so I have some independence in how I choose the size of the switch. Once I know the size of the switch, I know the output power that I want, I know the supply voltage, I can determine what the matching network will need to be. Of course, if I wanted to make this more complex, I'd probably add the matching network losses in, throw it into MATLAB, and have an optimization script that would optimize this. For back of the envelope calculations, this is fine. You could also throw in something and say, well, the matching network is going to have, I don't know, 80% efficiency. It's a reasonable assumption to start off with and calculate it. All right, so a practical CMOS design for a Class E power amplifier looks something like this. Now, you'll look at this circuit and say, this looks exactly like the linear amplifier did. The topologies, the circuit topologies are often the same. We're making a matching network that's going to be a downward impedance transformation. So I'm using a tapped capacitor match here. You can use other matching topologies. You typically want to minimize inductors like we did before, all of those kinds of things. But you know, the circuit itself might look the same. The couple of keys here. In practical CMOS circuits, this is not a choke. I'm optimizing these components so that I have B opt presented to the drain of the transistor, and that B opt is equal to BCD plus B drain parasitic minus the susceptance of the inductor VL. Inductors have negative susceptance, right? Looking in this direction from the matching network is designed to transform 50 ohms to an impedance that's equal to R opt plus JX opt. So I can have my matching network absorb, making the impedance transformation to a real value and leaving some excess reactance that's going to be used to delay current. So it needs to be a positive reactance. And then typically, in most CMOS designs, especially if I'm trying to achieve high output power, this power transistor is probably going to be a cascode. And it's a cascode because we need to protect the transistor from high voltage swings at the drain. So remember, one of the problems of the Class E network, we're doing a pulse shaping. So we're taking something that used to look kind of sinusoidal, and we're squeezing it and changing its pulse so that we get the zero voltage switching conditions. That tends to peak the waveform. So one of the problems with a Class E amplifier is the waveform can be peaked to be something at 3 point something volts, or 3.3 times the supply voltage. So the drain voltage can rise to be quite high. If we cascode the devices, we can protect them a little bit. Also in a practical sense, if we make the inductor not a choke, you can also show that that serves to reduce the drain voltage peaking a little bit because we're allowing the current to peak instead. No matter what you do, you can make a Class E network if you just follow the waveforms that they made, or that the SoCals made in their original paper, were zero voltage switching. You could make other forms of Class E networks if you just followed the simple rules that says that the drain voltage can't rise until the switch turns off. And it has to return to the derivative. It has to return to zero, and the derivative has to return to zero before the switch turns on. Those kind of things. So if you follow those rules, it's technically a Class E. Okay, let's talk about efficiency. Any questions so far? Okay. All right, so ideally, the efficiency is 100%. If we've done our jobs very well as circuit designers, we've managed to get the waveforms to not overlap. And so we don't dissipate any power in the transistor. All the power that we do generate is transitioned to the load. Great. Of course, in reality, we know that we have some finite switching resistance in our switch, so we have that ohmic loss or conduction loss. Our matching network definitely has loss. Another form of loss that's maybe not as obvious, but when we have a big power transistor, we have a lot of metal between the gate and the drain, so we actually do have a fair bit of overlap capacitance. And that overlap capacitance goes across the drain here. And remember, if we have a switching like waveform happening at the gate, we can't change the voltage across the capacitor instantaneously. So if I have a rising pulse here, I'm going to get a rising pulse immediately at the output. So my voltage waveform is not going to possibly be able to go to 0 before I turn the switch on, because I'm going to immediately, cause that pulse to feed through. So this causes a feed through from the input to the output. Yep.
Well, so in order to fix this problem, there's going to be 2 transistors stacked on the cable. More one switch.
So the cascode helps this to some degree. If I put it, if I stack 2 devices, because I don't have the immediate gate to drain feed through, but it's still layout. This is layout parasitic dominant, and so there's still going to be some gate to drain feed through, no matter what you do. So even if you stack the devices, there's going to be something, just because of the layout. It might be a minor effect. If you've done your job well, CGD should be hopefully a fairly minor effect, but can be important. And then, one other thing that we really have to think about is that these things all have a finite turn on time, or turn on or turn off time. So the original supposition for the Class E amplifier was that we could we could instantaneously turn the transistor on and instantaneously turn it off. If there's any finite slope in those turn on and turn off voltages, then there's going to be some VD and ID overlap, and that means that we're going to dissipate power. I'll upload a paper or two that they actually quantify the SoCals and Frederick Robb, who did a lot of work on the Class E's back in the day. They actually quantify these things, and you can kind of eliminate one variable at a time and quantify the impact of turn on time, CGD, those types of things. And they did this all before they could use Wolfram alpha to solve integrals and things like that. So they were really dedicated. Okay, so the effect of this feed through, if we kind of look at it as a circuit, the voltage here is going to shoot up immediately, and then it's going to kind of go back down due to some RC, like a time constant that has to do with the total capacitance or total resistance that capacitor sees. If we look at the impact on the waveform for this CGD effect, ideally what's happening is our switch, our voltage looks something like that, but in reality we get this little spike and then it kind of dissipates again. So you can see you have some potential for drain current overlap because of that. And then, of course, the finite turn on time. We're just saying, like, I've got this period where I can be dissipating power that my theory didn't anticipate. So when we examine efficiency, what's the practical efficiency of a Class E network? We basically take the output power divided by the output power plus all of these non-idealities. Now, I'll say that even though we added all of these non-idealities, and this is typically still going to be better than you can do with a linear power amplifier, because CMOS is good at switching for the most part. So we are good at switching. It does have relatively low parasitic, even though we're making giant power transistors. So you can expect to see efficiencies for RF amplifiers in the 60 to 80% ballpark. For just a switching amplifier by itself. Depends on the power range and the frequency you're operating at, of course. Now, one big thing about the Class E network is that it is a network that likes to be switched very hard. So, rail to rail very quickly. But it does perform fairly well even when it's not ideal. So they call a class of amplifiers non-optimal class or suboptimal Class E, where I've got a Class E like network that's shaping the wave something like a Class E, but I have all these non-idealities, and it actually holds up pretty well to that. Even in one of these SoCal papers, I'll upload a few of these. They show that even for quality factors as low as 1, the Class E network maintains an efficiency greater than 90%. So even if I don't have a very high quality matching network, I can get very good performance out of the Class E. Okay. Any questions? All right, so this paper, the one that I highlighted for Class E, they call this a series Class E. There's an additional type of Class E they call a parallel Class E, and it really just kind of changes the a few fundamentals of the design. All right, so let's look at our original series Class E network. In the original one, this was a choke. And then we had this series circuit. Okay. Now, my paper on Class E is from 2000. When was that? 2007, maybe 2009, 2007. I don't know. I'll post it. A long time ago. We showed that choke, that not using a choke is actually beneficial for CMOS circuits. It actually does help you to reduce the peak, the drain voltage overshoot that you get from the Class E shaping. But nonetheless, typically that inductor would have been fairly large. And, the challenge is that it's impossible to integrate a choke. How many of you have been playing around with the PDK, the 22 nanometer PDK? Like, what's the largest inductance that you found that works at a few?
6 or 8.
Yeah, something in that ballpark. And then you're going to have a fairly low self-resonant frequency when you do when you get that inductor. So I'll just say, you know, typically inductance has to be less than 10 nanohenries on chip. And 10 nanohenries is just a massive inductance. Like it's a total waste of chip area.
What's your definition for choke? Like, is it 10 times greater than the right, or 100 times? Or not?
We typically kind of say like when the impedance is 100 ohms or something like that, it can probably be considered a choke. Now, obviously, it depends upon what's around it, but remember, looking down towards the PA, we have an optimum termination impedance that's going to be on the order of a couple of ohms. So if that's a few hundred ohms, then you know the signal is going to want to go in one direction and not in that direction.
Okay, and then what about like like a linear amplifier? Like, I mean, like an LA or something.
Same thing, same reasoning. If the impedance looking up into that network is high relative to the signal path, then my signal doesn't want to go towards that thing. It wants to go towards the signal path. All right. So there was an author named Grebennikov. He's written quite a number of textbooks on power amplifiers. I don't know if I'm saying his name correctly. I don't speak Russian. I think he's Russian. Hopefully he's not like Ukrainian or something like that. That would be maybe, anyhow, I should probably check that out before I say anything.
It could also be like Bulgarian or
something. Could be general Eastern European. Anyhow, he's a pretty smart guy, pretty smart PA designer. He came up with this parallel circuit. What does this parallel circuit look like? Well, he just made a couple of key modifications to the network. All right, well, it's not letting me change the color, so I'll change it later. Anyhow, what he did was he explicitly takes this circuit, which, you know, we kind of showed before as that combination of, drain parasitic, shunt capacitance, and shunt inductance. And that is now a parallel circuit, if you will. Okay, just like before, this L naught and C naught, this is resonant at the switching frequency. And he went back and resolved all the equations, given that I have that parallel network instead of using a series network. And he showed that R opt is now equal to so weird how sometimes it does. Okay. All right. It showed that R opt is equal to 1.365 times VDD squared over P out. And then L shunt is equal to 0.32 times R opt over omega. And C shunt is equal to 0.685 over omega times R opt minus whatever drain capacitance. This is the parasitic capacitance from the drain. Just from the device itself. Okay. So is this better or worse for us as PA designers? Something, I'll tell you, there's something immediately better. What's better about it?
Low inductor value.
I didn't catch that.
Low inductor value.
Small, so Rohit said small inductors. Is that what you're trying to say? Very difficult to use.
I think that's what he said, he said low inductance.
A low inductance. Okay, yeah, that's generally true. The inductors, I mean, they're definitely not chokes, but I told you a moment ago that we can definitely also reduce the size of the inductors in the series circuit as well, and still get it to work as a series circuit. I think the biggest key here, it's maybe not appreciated all the time, is this factor of 1.365. It's bigger, you know, remember for a class A or a class B amplifier, that's 0.5. For a series circuit, it's 0.577, which is better because what it tells me is I'm making the optimum termination resistance bigger. Here it's 1.365, so that's very good for us.
Why is it bigger than?
Because I don't have to make as big an impedance transformation to get down to that value. So my matching network losses will be smaller, and then I also I don't have as severe a division between the transistor and the load termination. All right, now this can't be extended to all frequencies because every practical device does have some drain capacitance, and that's ultimately going to set the limit on how on what size we can make C shunt. If the drain capacitance is bigger than we want C shunt to be, then we can't have this network formulation. Okay. And I want to stress anything that we can do to make R opt bigger, where it doesn't cost us anything, is good. Okay. Okay, now Grebenikov would have also helped us out with finding a maximum operating frequency for this device, and that's dependent upon the drain capacitance that we have. So the maximum operating frequency is equal to 0.798 times R out over CD times VDD squared. So, you know, ultimately what all this kind of leads to is we want, you know, C shunt has to be greater than or equal to CD. If it's not, we can't make this PA. That said, we can still make a suboptimal network. So if it's not, you know, if you do your calculations and find out that it's close, you can still do a suboptimal network, and it's probably still going to work pretty well. Okay. All right, so just quick comparison. When you're designing a Class E amplifier, we have in the series Class A formulation, we have, these are terrible colors. All right, so in the series class E network, the formulation is that we find R opt, X opt, B opt, and those are all given just by primarily what power out we want from the device. Forgetting an omega here. And then in the parallel circuit, we just have our C shunt. And remember, the purpose of this matching network is just to present that R opt. We don't need to worry about the X opt in this particular case. That's already taken care of in the formulation. Oh, and of course, L shunt was equal to 0.732 times R opt over omega. These are really easy circuits to make. If you want to make a power amplifier, nothing easier in CMOS. You don't have to have a bias circuit or a driver. You just have to have something that'll switch the gate, and then you plug and chug formulas. Now, there's a lot to be done to optimize the designs, but if you want to make a first pass success, pretty easy to make a Class E power amplifier. Now, I've already made my comment that these, we call them power amplifiers, or they're called switching power amplifiers, but they are not amplifiers. There is no gain in the circuit. We are driving the input rail to rail, and the output is not proportional to the signal swing. If I, for instance, instead of driving 0 to VDD, drive the input from 0 to VDD over 2, is the power going to be different? It will, I promise. I'm modulating switching resistance, right? Because it's dependent upon the gate to source voltage. So the output power will be dependent upon a second order effect, the switching resistance. I'm not going to see a linear change in the output power just by changing the amplitude drive. Okay.
Professor, I have one question here. So what if I connect the C shunt to power VDD instead of ground? Because in small signal, it will basically stay in parallel as well.
Yeah, it's not, that shouldn't be a problem. As long as the voltage isn't changing, I don't think it'll be a problem.
Okay.
He asked if instead of connecting this cap to ground, he connected it to VDD. I think in principle that'll work. I don't see any reason it wouldn't work, but you need to think about that. Why would you want to do that?
It looks like an LC tank, so I feel like, what if I connect it to power? So it's just a curious mind.
Well, there could be, so depending upon, so the total impedance of that node is really just the shunt combination of all of those parallel items. So it wouldn't be a problem, but do remember that at least some portion of that capacitance is innately going to go to ground because it's coming in parallel with the transistor. I don't think it matters, but I'd want to see what the impacts were. Might change something subtle that I'm not thinking about.
Yeah, I actually tried it, but I found the same result, same gain, same everything.
Yeah, I don't see a good reason why it would be different, but there might be something subtle. Okay, So I just wanted to make a couple of comments. I already kind of started hinting at this, but one of the nice things about the Class E network is that it technically will work with relatively low quality factors. Now, in the original paper, they assumed that the quality factor of the network was infinite. And so they want the quality factor of the network to be infinite, because ultimately what they want is that only one tone can pass through this system. I put that tone at the input, and the system is going to perfectly filter out everything but a sinusoid being delivered to the load at the output. So that means I need to filter everything perfectly. All right, now we know that the quality factor of this network is equal to the reactance over the resistance. So we can do this in terms of inductance or capacitance. In terms of inductance, the quality factor would be omega times L plus L naught. This is the portion of the inductance that's part of the series resonant network, and then the portion that's part of X opt divided by whatever R opt is. It's a series resonant network. And we can go back and, we know what X opt optimally is, so we can solve for what LO, which is the portion that's going into the series resonant network, is. That's equal to R opt times Q network minus 1.1525 divided by omega. And then this would mean, because I have a series resonant circuit, the resonant frequency is equal to 1 over square root of L naught times C naught. I solve for the inverse of that, and I find that C naught is 1 over omega squared times L naught. Okay. Now, we are ultimately limited by loss in our matching network, but in terms of like how large the quality factor of the network can be, we know if we were to make the matching network have a quality factor of infinity, it would actually be pretty bad for us, because the matching network, because we have finite Q in our passive components. So all those inductors are actually lossy as well. So we have some additional loss in the matching network the higher that we make the quality factor. So this is okay, and it's okay for another reason. I typically don't want a circuit that only works at exactly one frequency, right? If for no other reason than when I make a practical amplifier, I'm going to get some PVT variation. And if I tune it so that it only works at 2.4 gigahertz, and then I'm off by 5% just due to statistical variation, now my radio doesn't work very well. My whole system doesn't work very well. So, okay. Yeah, so if we, just as a for instance, if we're looking to work in the Wi-Fi bands, right, we have to cover 2.4 to 2.48 gigahertz if we're in the lower ISM band, and if we're in the uni bands for the higher Wi-Fi frequencies, we might need to cover, say, 5.25 to 7. I think it's 5.25 to 7.15 might be off by a few megahertz there, one direction or the other. But anyhow, something like that. We have to cover a span. Okay. And then something I mentioned earlier that was shown in some of the original Class E work. right, so you can make your Q network as low as 1, maintain 90% efficiency. So it's suboptimal class E, but it's still good. And that's kind of nice. A Q network as low as 1 implies that we can have a bandwidth that's spanning, something like an octave, or something close to that. So you can have a really wideband circuit and still get good performance across that entire band. Okay. I had these two paper references as additional references that talk about the losses and suboptimal class E and things like that. I'll post them to the Canvas a little bit later. Okay, now, much like the linear power amplifiers, we can still benefit with a class E by making a differential circuit. So we can make a differential class E. We get a few key benefits. Remember, R opt differential is equal to 4 times R opt single-ended. This is for the same output power. If I want to deliver the same output power to a differential load, I can have an R opt that's 4 times bigger than if I was delivering it to a single-ended load. So that's good. I can still cascode. I probably still want to cascode because I want to distribute voltage stress. And so my network now might look something like this. I probably have some drain parasitics. Plus, I might add some additional capacitance at both nodes. And then I am just going to add a differential matching network. And the goal of this network is, I'm just going to say, to present Z opt for class E, and this could be for the parallel circuit or the series circuit. I might need to, I can design it either way. If it's the series circuit, I'm going to try and present R opt 0.577 times VDV squared over P out plus X opt. If it's the parallel circuit, I'm just going to present R opt, which will be 1.365 times. So the fundamentals are still the same. This differential impedance might be 100 ohms, it might be 50 ohms, depends upon how we're designing our interface to the circuit, but I'll say it's 100 ohms for the time being. And one other nice thing about switching amplifiers, and this goes even if we were doing the single-ended version of this, these two cascoded devices, they don't actually, they pretty much actually just sit in triode. They don't really transition back and forth between off and triode like the other ones do. They just kind of sit in deep triode. And that means that they don't need to be fast. So if you want to distribute more voltage stress across those two devices, you can make these thick gate IO devices. They don't need to be fast. And in your particular process, if you're looking in the CMOS 22 FDX library, you'll see FETs that are called EG, NFET. The EG is, I think, extended gate NFET or something like that. But anyhow, it's a higher voltage tolerance device, so you can use a higher voltage tolerance device there and distribute stress. There are a few pros to going differential. They're fairly similar to what they were for our linear power amplifiers, what's good about going differential?
Odd even harmonics will be cancelled out.
Yes, even harmonics are canceled. Anything else?
Common mode will be cancelled.
Well, I would say that's true, but remember, we don't really have any active gain in this circuit, so I'm not too worried about common mode. But I suppose from the following stage, if I don't want to pass some DC level to the following stage, that's good. I'll take it.
The whole output swing.
Yeah. So really, what we find is the biggest benefit there is higher R opt,
High voltage.
and in our case, we're also going to have higher voltage tolerance because we cascoded. But I don't think that's necessarily part of the. I won't say that's part of the differential circuit so much as the cascode. Okay, what are our drawbacks? Biggest is layout. We have now these giant power transistors, and the power transistors are going to be huge. They're going to be on the order of a few millimeters of periphery. Now I need 2 of them. If I cascode it, those devices need to be massive to keep the switching resistance down. So I've got a lot of transistor periphery. This is big, and it needs to be symmetric. Everything needs to be symmetric to make sure that I get the benefits of the differential circuit. Okay. And because the devices need to be big, or especially if I'm cascoding, I might be using I/O devices in something like this, I'm inherently going to have a bigger CD, so that drain capacitance, and that means might not be able to implement the parallel circuit. Okay. Yeah.
And linear amplifiers, I've seen the cross-coupled capacitor from like gate of one side to the drain of the other to produce like the S1 tube. Like that, could we do the same thing here to prevent that like voltage spike that we say causes some like extra?
Yeah. So actually, there was an interesting paper. It was by one of Paul Gray's students. I'll just see if I can dig that paper up. But we're not doing it to cancel the voltage spike. In this case, they actually are using it as a boost because if you cross-couple the capacitance, the rise in the drain voltage on the one side can be used to kind of boost the gate voltage on the other side. They're operating anti-phase from one another. So that's what they did it for. Not to cancel the feed through, but to boost the effective, or it reduces the switching resistance effectively. I'll see if I can find that paper. Can note to remind myself. Do you all know who Paul Gray is? He took analog. He's my grand advisor. He's my PhD advisor's PhD advisor. He wrote a famous analog book, or a book on analog CMOS design with Bob Meyer, who was another professor at Berkeley at the time. Yeah.
You don't talk about your advisors as much as Dr. Bob.
I don't.
No.
Dave, actually, interestingly, Dave is coming, my advisor, Dave Allstott, is coming to campus in a few weeks. see if I can get him to come to class, but I don't know. But he's visiting because he was on the faculty with Chen Ching Liu, who's retiring in a few weeks. So he's coming to visit for that. All right. Dave was a hoot in class, I have to tell you. All right, I have a couple of papers on Class E power amplifiers. One was in JSSC in June of 2009, another one in September of 2009. I expect all of my PhD students to publish at this aggressive a pace. It's mandatory. Yeah. That was it was a stressful year. 2 revisions going on simultaneously. Almost every paper that goes into JSSC is a major revision after the first pass. So, all right. A couple of the keys from these 2 papers, and I won't go into them too much, but one of the biggest things is even in the series circuit, you don't have to make this inductor a choke. Really what we're saying is that the susceptance of this inductor can be greater than 0. If it's a choke, the susceptance would be equal to 0. The reactance would be infinite, so the susceptance would be 0. That doesn't have to happen. And then I think I was one of the first people that kind of uncovered not necessarily the parallel circuit version of this, but the fact that really all that we need is this total parallel network. We just need to find a B opt that's equal to, B of some C external plus some drain parasitic minus the inductance. I think I was one of the first people that found that. I'll give myself some credit. And then other than that, everything is standard. As I said, the matching network is just designed to present R opt plus JX opt. And what I did specifically in the 2009 paper, the June of 2009 paper, was showed when you combine all these things together and use the thick oxide device, you can get the drain voltage to be less than or equal to about 2.5 times VDD. So remember, the Class E network by itself is going to give something like 3.6 times VDD at that drain node. When you do all these things, you can get it down to 2.5 times VDD, which is a lot better for device stress. Now, at what cost? Well, when we make that inductor small, ultimately what we're saying, when we turn the switch on, what we do effectively is ground the bottom of that switch, so the inductor is tied between VDD and ground. So the drain current is equal to 1 over L times the integral over half of the period. That's when the transistor is turned on. Times the supply voltage times dt. And so, ultimately, if we make this not a choke, that means more current. Not a problem. We're making these switches massive. We're making all the metallization around it massive. We're trying to reduce the switching resistance. So it's actually not a problem, but we do have to be aware that we are pushing more current through it. If we aren't careful enough when we do that, we might exceed some type of electromigration limit for the metallization, whatnot. So you do need to be aware of the fact that the current is going to go up when you do all these things. Okay, let's see. I think we will go ahead and stop there for the day. I'm going to start a new topology of switching amplifier tomorrow, and then next week we'll do another one. So there are 3 primary topologies of switching amplifier. There's class D, class E, and class F. D is maybe the simplest one. We're going to save that for last. I'll do class F first. All of these things are pulse shaping networks that are trying to keep the drain voltage and drain current from overlapping at the transistor. And that means that the transistor doesn't dissipate any power. None of them are amplifiers. We call them amplifiers. They're amplifiers in name only. There's no gain. We're just switching something. They are closer to being. The explanations for them are all closer to things that you might explain from a power electronics class than they are from an analog or RF class. But class F, in principle, what we're doing, is we're going to try and shape the waveforms. Well, I'll go back over this but we're going to try and shape the waveforms so that we have a square voltage waveform and a half rectified current waveform. We're going to do that using harmonic terminations at the drain. So that's the trick for class F. I should also say that all of these amplifiers have inverse versions, and what that means is I can invert the waveform. So in the class E that I showed you, where we have that 0 voltage switching, I can do the same thing and make it a 0 current switching waveform. That would be called an inverse class E network. Do the same thing for a class F network. I invert these 2 wave shapes, and I have an inverse class F network. Okay, so we will stop there. Any questions for me before we go on the online in class?
We're extremely complacent.
All right, good. Hopefully no more travel for the rest of the semester for me. So finish strong. Okay. All right. Thanks. We'll see you on Wednesday. Hopefully Cadence is working again by then. I'll talk to y'all later.